Well, before we actually get into the idea of implicit differentiation, I want to remind you of a few things. There are several ways that we can call for finding the derivative. For finding the derivative of y with respect to x. A little later on, we'll maybe see some with respect to other variables. Call for finding the derivative of y. And one way, of course, is that we've seen the notation dy over dx. And that's really read the derivative of y with respect to x. Now, a variation of that is this format, and the d on top is read as the derivative of what is in the brackets y with respect to, that's the denominator dx, so with respect to x. And then, of course, another shortcut notation is this. Your book may use some different notations, but these are the three notations that I would use most likely. Now, again, before we actually get into implicit differentiation, one of the most basic features or pieces that we need to understand is how we find the derivative of something like, we're going to be faced with this. How do we find the derivative of, say, y to the fifth with respect to x? That's the big question. And see, we don't have a problem saying what's the derivative of x to the fifth with respect to x. Of course, that's just 5 times x to the fourth. The issue that we have, though, is that our function is defined in terms of x, and so it's a critical issue that this with respect to and the variable here are the same. When that's not the case, then this causes trouble, say. That causes a problem. Causes a problem. And so we need to know how to deal with that problem. And so to deal with that problem, I'm going to just give an example. That's really what we're going to be faced with, is how we deal with the derivative of some variable other than x to a power. So let's suppose this is suppose we're given that y is 3x squared plus 1. Okay? And then we're asked to find the derivative of y to the fifth. Okay, well, how would we do that? Let's just do that then. The derivative of y to the fifth with respect to x. See, here's the situation. We know y is some function of x. It's just not written that way here. So our first step would be, of course, to replace that y with its 3x squared plus 1. And so that's to the fifth power. And then we recognize that that's just an application of the chain rule as the general power rule. That is, we bring that exponent down, don't we? Okay. And reduce the exponent by 1, so it'd be a power 4. But then we also have to remember that we multiply with the derivative of the inside, and the derivative of 3x squared plus 1 is just 6x, isn't it? Now, here's the significance. Here's what I want you to recognize. Let me come down here so we have some room. 3x squared plus 1, what we have right here is nothing more than y, is it? So it's just y to the fourth. See, we have a y and then the fourth power on it. And then the next thing I want you to recognize is that the 6x came from finding the derivative of 3x squared plus 1. See, that's where that came from, isn't it? And that's 6x. But this is nothing more than y, isn't it? So this is the derivative, if you will, of y. Is where that 6x came from. And of course, we could call that dy dx, or derivative of y with respect to x in that fashion. And so what I'd want you to recognize here is that what we've got in that 6x position, is nothing more than the derivative of the original y with respect to x. Or another way we could write that is 5 times y to the 4th times y prime. Now, that is the big conclusion here. And let's say this more generally, or in this fashion. When we're faced with the derivative of a variable other than x to the 5th power, that is, we're taking the derivative with respect to x, but the variable that we're taking the derivative of is not x. Well, then we have to think in the fashion that the y stuff in this case is really an expression in x. We just don't know what it is. And so we think of the y as being parentheses. And so what do? We bring down that 5, put it in front of the parentheses, and then we put a new exponent on the parentheses. That's the y. And then we find the derivative of what is inside the parentheses, and y is the parentheses. It's what's inside the parentheses. And so we'll go through that process when we see something of this nature. Let's do another example real quickly, though. Suppose we had the derivative of, let's say 7y to the 2nd power, but we're taking the derivative with respect to x. Well, what we would do is we would multiply you see, this is what we're thinking, okay? And although this is not what we have, we're thinking 7 times parentheses squared. See, our y is this stuff in there, isn't it? And so what do? We say, bring down the 2 and multiply with the 7, that's 14. And then we have our parentheses, but just to the 1st power. Remember, that's the y stuff. And then we take the derivative of what's in the parentheses, see? And that's just the y stuff. So this ends up being 14y, that's the parentheses, times the derivative of the y stuff itself, okay? That's just the stuff in the parentheses, which is represented by y. Well, let's do another example. The derivative of, how about, let's say 15y to the 3rd power with respect to x. That's the critical issue here, that is respect to x. Well, what we would do is we'd bring down the 3 and multiply with the 15. That's just normal, isn't it? And so, so we'd get what, 45? And then we reduce the power by 1, but remember, this is really y is like parentheses. It's got stuff about x in it. So then we have to multiply with the derivative of what's in the parentheses, and that's where we represent dy dx. And again, we could write that derivative of y with respect to x just as a y prime, and we might find that useful in the future. Okay, well, let's jump into doing a problem then. Let's talk about this idea of derivatives again. Now, what we've been doing, by the way, in the past, this discussion is about implicit differentiation as opposed to what we've been doing, which is explicit differentiation. So, for instance, okay, let's do this. We might be asked to find the derivative of y with respect to x for 2x plus 3y is equal to 5. So that's what we might be asked to do. Now, as of now, the only thing we know how to do is explicit differentiation. It's never been called that before, but that's what we've been doing. And what explicit differentiation is about is that we know what y is specifically in terms of x. See, we know the value of y. So if we're going to use explicit differentiation, we would have to have it solved for y. That's the only way we've been able to do this. So in this case, if we took the 2x plus 3y equal 5 and we began solving for y, first thing we would do is subtract 2x on both sides. And then we'd multiply, we could say divide, but I prefer to multiply here so that I don't have to deal with a complicated fraction. So I'm multiplying both sides by 1/3. So I end up with y is equal to 5/3 minus 2/3 times x. Well, now I'm prepared to find the derivative of y with respect to x because I know what y is. So derivative of y with respect to x is nothing more than finding the derivative of 5/3 minus 2/3 x. And of course the derivative of 5/3 is just 0, and the derivative of 2/3 x is just 2/3, isn't it? So we end up with 0 minus 2/3, or just a negative 2/3. Now, what I'd like to do is to compare this to implicit differentiation. So we're going to do the same problem, but we're going to do it implicitly. And what implicit differentiation is, or what it means, is that we can still find the derivative of y with respect to x without having the equation solved for y. So in this case, we can solve for y, but there are going to be examples in the future where we're not actually able to solve for y. We don't really know what y is in terms of x, but we can still find the derivative. So here's the way this would go. We would start out with our, it's the same problem. Like I said, it's find derivative of y with respect to x for 2x plus 3y is equal to 5. Now, what we're going to do is we're just going to apply the derivative operator. That is, we're going to take the derivative of both sides of this equation. I mean, if the two sides are equal, then certainly the derivatives of the two sides are equal. So that's the first thing we do, is apply the derivative to both sides. Now, on the left-hand side, we have the derivative of a sum. Okay, that's that. When we have the derivative of the sum, we simply take the derivative of both parts and add them together. That's the sum of the derivatives. So the derivative of 2x plus the derivative of 3y. And of course, on the right side, let's get this out of the way. The derivative of 5 with respect to x is just 0. Derivative of constant 0, isn't it? So we'll need to, we haven't been writing 0 in most of the time recently, just because we kind of mix it in with the rest of the answer. But in this case, we have it on one side of the equation, so we need to put that 0 there. Now we go back to the left side. And the derivative of 2x with respect to x, and there's the critical issue, that the variable that we're taking the derivative of is the same as the variable in the dx, okay? And that means it's a normal derivative. So the derivative of 2x is just simply 2. No ifs, ands, or buts about that. Okay, so we get a 2 there. But now in the next derivative, we have the issue that this is a different variable than what we're taking with respect to. But we still, one thing we do have is the derivative of a constant times a variable. And so that we've learned a long time ago that's the same as the constant times the derivative of the variable. Okay, so, or the expression, or the function. So we can rewrite it this way. And then, as we said at the very beginning of this lesson, the derivative of y with respect to x written this way, we can actually rewrite that and put it as a dy over dx. That's just another way to write that. Or we could have even said, instead of dy over dx, we just could have called that y prime just as easily. Okay, and see, and recognize that we're looking for y prime. Okay, well, here's the next issue, is that remember what we're trying to do. See, let's keep this in mind. We're supposed to find the derivative of y with respect to x. And so we've got an equation that involves that. And so what we're going to do now is take that equation and solve. We think of that dy over dx like an unknown. We're going to solve for that unknown. And so to do that, we need to get rid of the 2 that's on the left side by subtracting it from both sides. And of course, 0 subtract 2 is just negative 2. So we get that result. And then, of course, we're thinking of that dy over dx. That's what we're solving for, so we need to get rid of that 3. So we'll divide on both sides by 3. You know, we'll take this extra step, but we're going to take this side and divide by 3. And, of course, take this side and divide by 3. Well, what does that result in? The 3's cancel here, and we have then solved for dy over dx. It's negative 2/3. And I'm sure that this hasn't gotten past you, but we got exactly the same result. And we did it implicitly in the second half of this page, that we did not have to know exactly the value of y in terms of x. We could still find the derivative of y. Well, this is the introduction, and what we'll do now is look at several other types of examples where we have to use implicit differentiation.